Hello and welcome. This is SFU Math 232. My name's Brenda. We're looking at today's section 7.7, the projection theorem. So we've actually, this last few lectures, we've had a number of theorems in a row, sort of one theorem per section. So let me just remind you of the ones we've just recently seen. We've seen the dimension theorem. Sometimes that's also called the rank nullity theorem. We've seen the rank theorem. And we've seen the pivot theorem. Okay, so maybe stop the video and just see if you can write out what those are, because they're fairly easy to state, and you want to be able to make use of them whenever you need them. Okay, now let's take a revisit about something that we have actually seen earlier in the course. We did look at orthogonal projections onto lines in R2, and we had derived the matrix for doing that. So I'm just going to remind you of what that looks like. We have a line through the origin in R2, and that line makes an angle with the x-axis, which we are calling phi. And then we imagine taking a vector, let me just call it v, like that, a vector v, and then we want to understand what the orthogonal projection of that vector is onto the line that I've drawn. So that is this guy here. I'll just label that v1 there. So we sort of imagine a light source here with the rays coming in perpendicular to the line, to this line here, and then we would see the shadow v1 would be the shadow of v on the line. Okay, so what happens if we don't know the angle? I mean, presumably if we were given a vector or something like that, like the line as a span of a vector, we could compute the angle. But the idea is, can we compute the projection given that we get the line given to us like this? So the line is the span of some vector A. Can we find the formula for the orthogonal projection onto L without calculating the angle phi? Okay, so what we're saying is this line here, this guy here, is the span of a given vector A. Okay, it's a one-dimensional entity. Okay, so what we do is we have a vector V, and we want to find the projection of V onto the span of A. Okay, so let me just draw another picture here. I've got the span of A. I've got V, and I've got V1 right there. Okay, we can see right away that, I mean, V1 is on A, on the span of A. So that means that V1 is equal to some number T times A. And I could call for, I don't know, I could call this W, for example. All right, I could also see that there's another vector here, V2, right there. And then you could see that V1 plus V2 is V. So that means that V2 has got to be equal to V minus T times A. And that V2 is orthogonal to V1, and V2 is also orthogonal to A. V2 orthogonal to A. All right, V2 is orthogonal to A. That means that V2, which I'm going to write in this way, dot A must be equal to 0 because they're orthogonal. So this is another, V2 is orthogonal to A. That means the dot product of V2 with A is equal to 0. Okay, so I can distribute that out. V dot A minus T times A dot A is equal to 0, and then I can solve for T. That gives me that T is equal to V dot A divided by A dot A. And then that allows me to substitute in, here I'll show you where that, I'm going to put that. I'm going to substitute this value of T here into here because I'm trying to find V1. So V1 is equal to T times A, and I've just figured out what T is. It is V dot A divided by A dot A, and now I multiply by A. So that's T, and then I multiply by A, and then I rewrite this, and that is V dot A multiplied by A divided by the norm of A squared. Okay, A dot A is the norm of A squared. And then that is V1, and that is our orthogonal projection. So then I can just write that in a fancier way. The projection of V onto A is equal to V dot A divided by the norm of A squared times A. Okay, this gives me a method of computing the projection of V onto the span of A without computing that angle phi. Okay, let's see that. I think that's written on the next page here, possibly as a theorem. So there it is, x dot A. Okay, there it is here. Okay, so using x instead of V. So we've got a theorem here, basically stating what we've just derived on the first page here. So we've got this non-zero vector, and well, we're going to actually say one thing, and that is that vector can be expressed in exactly one way, and that is x1 plus x2, where x1 is the orthogonal projection and x2 is in the orthogonal complement of A. Okay, and then the two vectors are given in this way. We have here x1, that's what we just showed, and then we can easily compute x2 as x minus x1. So there we have it. Okay, so there we have it, written yet again. If A is a non-zero vector, and we have any vector that orthogonal, this is orthogonal, projection of x onto the line A, on the span of A, is denoted this way. The projection of x onto A, and we can compute it in this way here. And that's the component that's along A, and then the other component is perpendicular. All right, let's take an example. So what we want to do is figure out the vector components of x along A and x orthogonal to A. So again, just that picture. Here's A. It's the whole line. It's the span of A, like that. Here's x, like that. And we want to figure out x1 and x2. And the x1 is the component along A. As you can see, it's along the same line. And then x2 is orthogonal to A. Okay, so what do? First thing we're going to do is we're going to take x dot A. So we're making this calculation right here. So we're going to take x dot A. That is going to be 7 minus 5, 9 minus 1 dot 3, 0, 1, 2. And that comes out to 28. Then we are going to take the norm of A squared, and that is A dot A. And that is 3, 0, 1, 2, dot 3, 0, 1, 2. That comes out to 14. Okay, so then the projection onto A of x is 28 over 14 times A. And that is 6024, and that is x1 in our drawing. That is the vector component of x along A. Maybe I'll even write that for our first example. Vector component of x along A. And the next thing I'm going to do is calculate the vector component orthogonal to A. That's going to be x2. And x2 is x minus the projection of x onto A. And that is x, that is 7 minus 5, 9 minus 1 minus 6024. That is what we just found here, x1. And then when I do that subtraction, I get this, 1 minus 5, 7 minus 5. That's x2. So that is the vector component. So this guy here, that is the vector component of x orthogonal to A. Okay, so we can check ourselves a little bit. I mean, we know, when looking at our picture and of course knowing what we've calculated, it is of course the case that x1 dot x2 should be equal to 0. I mean, they're perpendicular to one another. So let's just quickly check that that worked out. 6024 dot 1 minus 5, 7 minus 5. I calculate that 6 plus 0 plus 14 minus 20, and that is 0. Tick. Good. And also that x should be x1 plus x2. That's vector addition. So let us just confirm that we haven't made any mistakes, that we get 6024 plus 1 minus 5, 7 minus 5. And that is equal to 7 minus 5, 9 minus 1. That's the sum. Okay. Okay. So let us then notice the next thing. When we saw this before too, we know that projection is a linear operator. But let's just remind ourselves of that. So we've defined this thing here. It's the projection onto the span of A, and we've already seen that in R2, at least from our previous section, that it's a linear operator. It works the same in Rn. It's a linear operator. That means we can represent it as a matrix. And in fact, we already knew that, and we saw it on the first slide in R2. Okay, so what matrix is that? So well, you can do the usual sort of thing. You can look at the standard basis vectors and figure out what those are, and then form the matrix, the standard matrix, using those as the columns. And that's what this, when you do that, you get this guy here. So this is the matrix, and you can write it in one of two ways, since A transpose A is the norm of A squared. Okay, so let's just take our previous example and find the matrix. So our previous example, we had A was this guy here, 3, 0, 1, 2, and we had that, well, we have that, let me just get down here, A transpose, 3, 0, 1, 2, there's A transpose, and we had the norm of A squared is 14, and we knew from before, we know the answer from before, when we try to project, well, we try to project x, which was what? Hang on, I have to figure out what x was, and we're going to try to project this later, and that was 7 minus 5, 9 minus 1, and we found that when we did project it, we got this guy, so we already know the answer. But let us try to form the matrix, and we only need A for that. We're not going to use X until we actually have the matrix. Then we're going to take the matrix P and multiply it by X, and hopefully get X1. That's our idea of what to do. Okay, so let's form P according to this here. So P is going to be this matrix. It's going to be 1 over 14, and we'll multiply 3, 0, 1, 2, multiplied by 3, 0. I really don't need the commas here. 3, 0, 1, 2. Okay, this is the outer product, and so that is 1 over 14, and then the matrix I get here is 9, 0, 3, 6, 0, 0, 0, 0, 3, 0, 1, 2, 6, 0, 2, 4. Conclusion wrote this down wrong. 6, 0, 2, 4. That's the answer from before. Okay, so I've got a matrix here. Now what I'm going to do, if I want to find the projection of any x, I'm going to choose this x, but any x onto the line spanned by A, I'm going to take P and multiply it by x. So I'm going to take this P, 1 over 14, and here it is 9, 0, 3, 6, 0, 0, 0, 0, 3, 0, 1, 2, 6024, and I will multiply that by 7, the vector I want to project onto A. There it is, same guy from before. And I make this calculation and I get 1 over 14 and I get 84, 0, 28, 56, and that simplifies to 6024. Thank goodness it's the same. Okay, so that's it as before. Okay, now next question, what is the rank of P? Okay, I mean, it should be fairly obvious. The rank of P is 1. Rank P is 1. First of all, it was formed via an outer product. And even if you sort of possibly forgot that, you can see by the way that P is being formed here that each one of the rows of P is a linear combination of this guy here. So each row of P is a linear combination of that. So there is only one linearly independent vector here, since every row is a scalar multiple. So this, let me just write it. This is another way of seeing this feature, that it's a rank 1 matrix. That is, every row is a scalar multiple of 3, 0, 1, 2. Okay, so we're going to do another example. Two ways of doing this. In this case, we are just going to go directly. It says here, find the standard matrix of the orthogonal projection of R3 onto the line spanned by a 1, 0, minus 1. So this is, we have then that A is a column vector, this guy here, 1, 0, minus 1. A transpose is a row vector, that guy there, and we can compute A transpose A, and that will be 1, try to be consistent here, 1, 0, minus 1 multiplied by 1, 0, minus 1, and that's 2. That's the inner product. And then the projection matrix that encodes this this linear operator is going to be this guy here, 1/2. That is 1 over this multiplied by the outer product of these same two vectors, and the outer product is going to be us multiplying these two together. That is 1/2. And we get this guy here, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Okay, so now to project any vector onto the span of 1, 0, minus 1, we simply multiply, we compute px. So if I take p and I multiply by x, what does that equal? That is the projection of x onto the span of 1, 0, minus 1. If you're setting something up like this and you choose A to be the unit vector, so your line is the span of a unit vector, well, that makes things even faster because the A transpose, this A transpose dot A will be 1. So you don't have to worry about that. Okay, so let's go ahead and find the standard matrix for projection of R2 onto a line through the origin. That makes an angle of phi with the positive axis using our newfound knowledge. This is our newfound knowledge. That is, okay, so what we're going to do is, let's just have a little picture of what we're doing here. We've got a line through the origin. It makes an angle here, phi. And then I'm going to have a vector along this line. There it is, that vector there. That vector is going to be u. I'm going to make it a length 1 vector, a unit vector. And then this line here will be the span of u. Okay. Okay, so I'm just drawing, u is still length 1. I just want to draw it a little bit bigger so I can actually work with it a bit better and in a different color. This is too confusing. Let me just draw that in black or something. So I'm going to just make this still a unit vector. That is u right there. So I just want to be able to show the components here. We've got a x component of u here and a y component of here. U is of length 1. So u is the vector cos phi sine phi. So now I can form the standard matrix for projection simply by taking the outer product of u and itself. So that is going to be here cos phi sine phi multiplied by cos phi sine phi. And I go ahead and do that calculation. I get get a matrix, cos squared phi, cos phi sine phi, cos phi sine phi, and sine squared phi. And that's exactly what we saw before, and it was reprinted on the first slide. So we can easily get this now by thinking of this in the right way. We already knew this, but perhaps if somebody asked you how to do a projection onto a line that's at angle phi from the origin, and you did not have this in your head, you would be able to regenerate this picture, realize what the x and y component are, form the outer product, and get the matrix. So maybe you don't have to memorize it. I try to memorize as least things as possible. Okay, now what we didn't do before and we can now do is we can generalize this up to higher dimensions. We did this in R2 earlier on, and we also did the rotation and the reflection. But now what we're going to do is we're going to say, you know what, we can do this projection in any dimension that we want. So we're going to then project onto a subspace, and we're not going to say what the dimension of the subspace is. So we have a subspace of Rn, then we are saying, we're stating this as a theorem, that every vector in Rn can be written in exactly one way, where x1 is in the subspace and x2 is in the orthogonal complement of the subspace. So the nomenclature is the same as we just did. So previously we had the projection. So here, we just write this. Previously, we had projection onto the span of A, where A was a vector. Now, this is a subspace of R2 of dimension 1. Now we are projecting a vector onto a subspace that might be 2 or more dimensions. So W will be some span of some number of vectors, A1, we don't know how many, 2, like that. That may be more than one dimension. Okay, and we can do that by calculating the projection matrix. That'd be this part right here. We can calculate that matrix from the basis vectors for the subspace. So we take the basis vectors for the subspace and we put those into a matrix M as column vectors. I mean, when you think about what we were doing from before, we had the basis vector like that, A. That was the basis vector for the subspace, right? That was the line. The line was T times A, and then we took here A transpose. So we're doing the same thing, but we're just allowing now for it to be, instead of just a single column, it is now a matrix where this matrix M is all of the basis vectors for W as columns. Okay, so it's the same thing. It's a projection. Okay, so there is the matrix identified as P. We're just going to do a little exercise here just to remind ourselves about some terms and maybe some things we haven't seen for a bit, sort of a little bit of a mental exercise. You actually, I think, would be a good idea. Stop the video and show that matrix P is symmetric and idempotent. Okay, so let us first make sure that we know what those two things are. So I'll just symmetric. What does symmetric means? It means that P transpose is equal to P. What does idempotent mean? This is Latin for same. So if you want to think of it, same potency. That is meaning that P is equal to P squared, which of course then means that P is equal to any power of P. So by taking powers of the matrix, you do not change what it does. It stays the same. Okay, we also saw this word here when we saw the word nilpotent. Okay, so that's what those two things mean. Now we have a matrix, here it is, and it's formed these things, and we want to show that it's symmetric and idempotent. So now is a good time to stop. We know what we want to show, and then what should we do to show that? So maybe try to stop the video and try it yourself, and then check back. I'm going to use the following things. This is what I like about, we're getting near the end of the course. We sort of start reviewing some of the things that we haven't maybe used for a bit. That is this: if I take the transpose of a product, that is equal to the product of the transposes in the reverse order. If I take the inverse of a transpose, that is the same as the transpose of the inverse. And if I take the inverse of a product of matrices, that is the product of the inverses, again in the other order. Okay, so these are three features that we have seen before. Okay, so let us just show that first we'll show that this matrix is symmetric. Okay, so we know that P is this M transpose M to the minus 1. So I'm going to take the transpose on both sides. There. Okay, and then with this property here, I'm going to take the transpose of each individual item, and I am going to reverse the order. So this becomes M transpose transpose times M transpose M. Yeah, I did two steps at once here. M transpose, this transpose minus 1, and M transpose. So when I took the transpose of this middle guy here, stayed in the middle, and then what I did is I simply exchanged using this property here, I exchanged the order of the operations there. Okay, now I can do some simplifying here. Transpose, that the transpose of the transpose is simply the matrix itself, and then here I can take the transpose of this product, and that becomes in the opposite order M transpose M to the -1, and then I've got here M transpose. Okay, and what's this happened? That is exactly P. So P transpose is P. So P is symmetric. Okay, next one, we want to show that that it's idempotent, and to do that we're going to show that P squared is equal to P. And so I will simply go ahead and take P and squared. So P is this guy here, M transpose M -1 M transpose, and I will square it. And that means, well, I'll write it out longhand here. There, that is P times P. Okay, now I'm going to apply the rules, one of these three rules above. So I'll do this one right below. That's going to be M, and then I apply that rule. So that is going to be then, let me think here, that's going to be M to the -1, and then M transpose to the -1. And then I've got M transpose and M. And then this is going to be, oh, hang on. Something went wrong when I wrote this out. Sorry about that. This is like that. So then that is going to have to be here M to the -1, M transpose to the -1, and then M transpose. And then what I see is that this thing right here is I, and then this thing right here is I. So this is equal to M to the -1, M transpose to the -1, M transpose. And that is equal to M. And then I put these two guys back together, and I get M transpose M to the -1, M transpose. Et voila, that is P. So P squared is equal to P. Sorry, I'm losing my voice slightly from doing these videos. Okay, our final example here. Hopefully I can hold up. No, we're going to try to find the standard matrix for the orthogonal projection of R3 onto the plane. So we have some plane oriented in R3. We want to be able to find a matrix such that we can then take any vector, multiply on the left by the matrix, and find out what the projection of that vector is onto the plane. Okay, so we've got the equation of the plane. So how we're going to do this is we're going to write this like this. And we're going to identify, like we usually do, that there's in the solution to this system, there are two free variables. I'm going to call yt and zs, which of course then allows me to write the solution set to the system of equations, which is precisely one equation. Write it like this: t times -1, 1, 0 plus s times 3, 0, 1. And so that plane, a subspace of R3, is the span of these two vectors. So those two vectors form a basis for the subspace that we want to project onto. So M is going to be a matrix whose column vectors form a basis for W. And that's I already know what those are. I've identified those. So I've got M. Once you've got M, the game is pretty much over, because it now becomes a pile of calculations, right? I need to calculate this this formula. I'm just going to wind back here. This formula here. So I have to take M, I have to multiply, I have to have the transpose, I have to take an inverse, I have to go ahead and do that. So I'm going to do that once. So I've got M. Let me just then identify M transpose. That looks like this: -1, 1, 0, 3, 0, 1. And then M transpose M is going to be -1, 1, 0, 3, 0, 1. -1, 3, 1, 0, 0, 1, and that is this guy here, 2, -3, -3, 10. Now I've got to take the inverse of that. Mercifully, it's a 2 by 2 matrix, so I'm going to take M transpose M to the -1, and then that is going to be this guy here, 10 out of 11, 3 out of 11, 3 elevenths, and 2 elevenths. Okay, so that's the inverse. You should, of course, be able to calculate the inverse of a 2 by 2 matrix. And then I will be able to compute P from these things. There's P. That is going to be M transpose M inverse. And M transpose. Okay, a bunch of multiplication. Biggest danger now, of course, is making some sort of arithmetic mistake. Here. There we go. Now I've got the matrix that does the projection. So now I can take any vector I want and figure out what its projection onto this plane is. Okay, so I feel excited when this happens, because I've now I can do any number of projections that I want. So now I can project any vector onto the plane x plus y minus 3z equals 0. So I'll do that with the one vector we were given. We were given a vector at the beginning here. That vector is 3, 0, 1. And so I simply take P and multiply by V. One more multiplication to do. So, whoops, there is P. And I am going to multiply that by V. And I'm going to get this guy here. First, I feel, I feel mild amounts of an alarm, because I wasn't necessarily thinking that was going to happen. What is this? So then I think to myself, what does this tell me? This tells me that the vector was already in the plane, because it didn't change. So it tells me that the vector was already in the plane. So then I think about that, and I think, okay, is that true? And then I look at how vectors in the plane are defined. They're defined like this: t times -1, 1, 0 plus s times 3, 0, 1. And then I think, oh, it is true that this vector was in the plane, because if I take t equals to 0 and s is equal to 1, I could easily see that the vector was already in the plane. So now when I projected something that's already into the plane, that's where I would expect it to stay. So sometimes when something happens that you can notice, you should be thinking, does that make sense geometrically, or can I see why that's the way, or have I possibly made some sort of an error? Okay, that is it for section 7.7. I will be back. We have three lectures to go, folks. We are near the end. Thank you very much. Bye.